A coin is tossed 62 times and 37 heads are observed. So what they're describing there is a number of trials and a number of successes. So we can calculate an empirical sample proportion for this problem. It will be p hat equals x over n, where x is the successes and n is the trials. So we'll do 37 out of 62. We can get a decimal for that. 0.597. Okay, so that's what's going to go here. They ask for the standard error in the estimate. So when you do a binomial type of problem, the standard error is going to be the standard deviation of the sampling distribution. That is the standard error. So a long time ago, we said that if you have a binomial question like this one, it would make a distribution which is discrete, but it would be somewhat bell-shaped. Okay, so this is like the original binomial distribution for x successes. And so if you remember way back, this thing had a mean of n times p, and then it had a standard deviation of square root npq. What we're going to assume here is that our mean for our binomial distribution will be n times p hat, and the standard deviation will be np hat q hat, because we don't know what the true population proportion is right now. All we know is the empirical proportion, but we assume that it's the proportion for the purposes of making the confidence interval. It's going to be the center of our interval, I mean. So when you go to make a sampling distribution, you get a bell curve like this. This one's called the sampling distribution. And to find his standard deviation, it's going to be called sigma p hat. And that makes this, which is this, which comes out to this. So that is the standard error. The whole point is that once you do the derivation, this is the standard deviation of your sampling distribution. So that is the formula that you'd want to use here for standard error. It's the square root of p hat q hat over n. So that's going to be a square root of 0.597 times 1 minus 0.597 over 62. 0.0623. So let's see, the next step will be to get a z-score for a 95% confidence interval. So we'll put a c of 0.95 in the middle. That'll leave us with 1/2 of 1 minus 0.95 and a tail. So that's going to be 0.025 in each tail. Then I could go to, I'll search for inverse normal distribution calculator. I'll use this first one that comes up, online stat book. I can do a left tail of 0.025, or I could do a center area of 0.95. So it's z-scores of negative 1.96 and positive 1.96. I'll just enter the positive version of it. The lower limit of the confidence interval is going to be found by getting the margin of error. So the margin of error will be ZC times sigma p hat, which is equal to ZC square root of p hat q hat over n. So that's going to be 1.96 times the square root of 0.597, 1 minus 0.597, all over 62. So my margin of error is 0.122. So now when I go to make my confidence interval, the center of the interval is p hat, so that's 0.597. The right side is p hat plus e. The left side's p hat minus e. .719, 0.475. So we're between 0.475 and 0.719. We're 95% confident that the true portion of heads is between 0.475 and 0.719. Based on these results, it is plausible that the coin is fair because that contains 0.5. The coin should be considered fair if 0.5 lies within the confidence interval, which it does. 0.5 would be somewhere over here. That is the fair coin probability.